In Screencast 7.2, we introduced the vibration isolation table, and this was a simplified model in which, on this table, which we would be doing delicate experiments that we don't want to be influenced by any outside forces. In this simple model, it had 2 degrees of freedom, we had a vertical translational degree of freedom, and then we had a rotational degree of freedom, theta. And in the screencast, we calculated the moment about the center of mass. So in this screencast, we're now going to look at the equations of motion that fall out of applying Newton's Euler's first and second laws to this system. A quick review of the reference frames that we used are an inertial reference frame with a basis E1, E2, and E3, and then a body frame with the basis B1, B2, and B3, and the origin of the body frame was at the center of mass. We have this transformation between the two bases, and then the angular acceleration of B as observed in the inertial reference frame as theta dot in the B3 direction because of the counterclockwise rotation. We also had a free body diagram that we used. There were 3 forces applied to the free body diagram: the spring at A, the spring at B, and then the force due to gravity, which is acting at the center of mass. And so here the spring at A is defined as the spring constant, the negative, multiplied times the change in length that we defined, and then the spring constant in B is negative, spring force at B is the negative spring constant multiplied times that change in length. So for a refresher of this, I encourage you to go back to Screencast 7.2 to take a look at this, and then the ending of that screencast was that we found the moment about the center of mass, which was due to these 2 spring forces. And so now to analyze the dynamics of this system, let's apply Euler's first and second law. So the first Euler's second law, F of g is equal to the mass, which you said m sub g, multiplied times the acceleration of the center of mass as observed in the inertial reference frame. So let's start with our translational kinematics. So our position vector of g with respect to O is equal to 0 in the E1 direction plus y in the E2 direction, and so the velocity of g as observed in the inertial reference frame is y dot in the E2 direction, and then the acceleration in the inertial reference frame is y double dot in the E2 direction. And so that takes care of our right hand side. We need to deal with our left hand side, which is the sum of all the forces. So the sum of all the forces is our spring force at A plus the spring force at B minus mg E2, which we lift off of our free body diagram. And then when we calculate all these, add them up, and then set this equal to the right hand side, we get this expression, which are the force of the spring at A, force of the spring at B, minus the force due to gravity is equal to the mass times the acceleration. And all of these terms are in the E2 direction, so this gives us our scalar equation of motion for the translation. And our equation of motion is the second order differential equation, so look for the y double dot term. This is our equation of motion for translation, and we can see that it's a function of y, and it also is a function of theta, so it's a coupled equation of motion. So we say that y double dot is a function of the translational position and the rotational position. No velocity terms in here. Let's apply Euler's second law to the system. So this will give us our equation of motion in the rotational degree of freedom. And so for our angular momentum about the center of mass, this is equal to the moment of inertia multiplied times omega of the body frame as observed by the inertial reference frame. This is equal to moment of inertia, which is a scalar, times theta dot in the B3 direction. And then the time derivative of this expression is equal to the moment of inertia multiplied times theta double dot. It's the only differentiable term in the B3 direction. And so now when we set the left-hand side, the time derivative of the angular momentum, equal to the center of moment about the center of mass, which you've already calculated, we now have a rotational equation of motion for the system. We know this is an equation of motion because we have a second order differential equation, theta double dot, and it's a function of the state of the system, and so we see that theta double dot is a function of, in this case, we have y, as before, and theta. And so now with these two equations of motion, we have enough information to solve for the state in both degrees of freedom, in our vertical degree of freedom as well as our rotational degree of freedom. And these equations are coupled together, and we see that because theta double dot is a function of both the translational degree of freedom and the rotational degree of freedom, and y double dot, that second order differential equation, is a function of the translation and rotational degrees of freedom. Now, these equations of motion that we have are not pretty, but let's see what we can do to gain some more insight into the motion of the system and considering what the system actually does. This is a vibration damping or vibration isolation system. And so whenever we hear vibrations, we should be thinking oscillatory motion. And we've solved the differential equations before for spring mass damper systems, and we'll be doing more with vibrations a little bit later. However, one of the things that we need to do in a vibration system is find out what its equilibrium point is, or essentially where the system begins. So let's take a look at that, and let's make some substitutions. To find the equilibrium point, we're going to substitute in y double dot is equal to 0, because this is like a statics problem. There's no acceleration in the translation, and there's no acceleration in the rotation. So y double dot is equal to 0, theta double dot is equal to 0. We would also say that y dot is equal to 0 and theta dot is equal to 0. But recall that in this equation of motion, there is no velocity terms. There's no state in which we have y dot or theta dot. And so we'll substitute that in, and then our equilibrium positions will be, we'll substitute in y is equal to y naught, and then theta is equal to theta naught. And so when we solve for y naught and then theta naught, the equilibrium position, we get this. And so let's consider the system now with these equilibrium values. So first we need to make some decisions on what types of springs we would use in this vibration isolation table. And so recall what we're after here. It's a table in which we can run experiments on top that are not influenced by external forces. So we see here that our choices on our springs make a difference in what the table is actually doing. We would choose springs that are the same in both legs of the table, and this shows us that our equilibrium position is going to be our resting length. So if we get the same spring on both sides, that it'd be the resting length with a little bit of sag due to the weight of the table. And then if we choose the same springs on both sides, then conveniently, and I think intuitively, we see that both of these terms go to 0 because our spring constants cancel, as well as our spring resting lengths cancel. And so our theta would be equal to 0 in this case. And so now after dealing with the geometry of the system, or putting it into equilibrium with a flat surface on the table, now let's deal with the vibrational component of the table. So in vibrations, we can often simplify our equations of motion because our vibrations usually have a small amplitude. So we'll simplify our equations by using a small angle and small translation approximations. And it looks like this, where we say that y we change to a small translation, and then we'll also change our we'll also use a small angle approximation. So we say that sine of a small angle is equal to that small angle itself, and then cosine of a small angle, so delta theta, is equal to 1. And when we apply these to our equations of motion, we get much nicer looking equations, of course, and this is considered linearizing the equations. We're only taking the first term of a Taylor series approximation, and with this information, we see a better breakdown of the problem. We still have a coupled equations of motion where we have y double dot is a function of the change in theta and the change in y. And theta double dot is still a function of the change in theta and change in y, with these scalars that are based on the spring constants. And then when we are once again making decisions about what types of springs we're going to be using in the table, if we choose to use the same springs on both legs, then we see here that our Ka minus Kb will cancel in each of these terms. And so now this greatly simplifies our system, where we have y double dot is now a function only of the change in the small translation y, and then theta double dot is only a function of the small change in angle. So by choosing springs that are the same on both sides, it's obvious to us now that this now decouples the system from each other. And so y double dot is a function only of y, and theta double dot is only a function of theta. And so you can see that in some systems, such as this table, we can be clever in how we choose our design, using our design variables in which we can uncouple the equations of motion. So that gives us a much simpler equations of motion for both degrees of freedom. We have theta double dot is equal to a scalar multiplied times theta. So this is a much easier system to solve, and we see this particular situation in vibrations in a lot of systems.